Today we'll talk about another interesting topic, refraction at spherical surfaces. When waves strike a spherical surface like a lens, what happens? Let's start with the basics. Let's imagine that this is a glass slab here and this is air surrounding the glass slab. So let's try to find out the equation when a ray comes and it gets refracted from this spherical surface. So let's say this is an object here which is emitting a ray that is striking the spherical surface and forming an image right here. This is the normal at the point of contact, and as you see, this normal at the point of contact passes through the center of curvature of the spherical surface. This is angle theta, the angle of incidence, and this is angle phi, the angle of refraction. So what will be the equation of refraction here in terms of mu1, mu2 and the image distance and the object distance? Let's find out. Let's assume that this angle here, the angle that the incident ray makes with the principal axis, is alpha. Let's assume that the angle the normal makes with the principal axis is beta, and the angle that the refracted ray makes with the principal axis is gamma. Now we already know that by Snell's law, 1 mu2, that is the refractive index of this glass with respect to air, is equal to sine theta divided by sine phi, where theta is the angle of incidence and phi is the angle of refraction. We've already studied this. Now if theta and phi are very small, that is, this incident ray is it's making a very small angle with the normal at the point of contact. It's almost perpendicular to the spherical surface. In that case, sine theta can be approximately taken to be theta and sine phi will become phi. Now we already know that theta here is equal to beta plus alpha. We know that from 10th class geometry, because you see, beta plus alpha plus this angle OQC here is 180 degrees, and similarly theta plus angle OQC is 180 degrees. So that means theta is equal to alpha plus beta. There you go. And similarly phi here will be equal to beta minus gamma, because phi plus gamma will similarly be equal to beta, and therefore phi will be equal to beta minus gamma, again by 10th class geometry. So this is our equation. So if you put mu2 by mu1 equal to beta plus alpha divided by beta minus gamma, this is what you get here. Now gamma here is pq by pi, because as we've already concluded, the angles alpha, beta and gamma are also very small. Alpha plus beta is equal to theta. Clearly alpha and beta too must be very small. So similarly gamma is also very small. Now gamma, if you look closely, can be taken to be pq divided by pi, because gamma will approximately be equal to tan gamma, which is clearly equal to pq upon pi if we take this arc to be very small in length, so small that pq can be assumed to be a straight line instead of an arc. I know we're making a lot of assumptions right here, but they generally do hold for small values of theta. Similarly, alpha can be written as pq by po. Alpha can be approximated as tan alpha, which is the same as pq by po. And beta, what is beta? Beta is clearly pq by pc, because beta can also be written as tan beta approximately, which is approximately equal to pq by pc. There you go. We've substituted the values. What is pi? Pi is clearly plus v, the image distance. As you can see, I is where the image is formed. P, as you can see, is the center of the spherical surface, so clearly pi will be equal to plus v. Now we have written plus because the positive direction is the direction of the incident ray, and since the incident ray is moving to the right, we've written the image distance as plus v. Similarly, po is the object distance minus u, and pc is the radius of curvature. We already know that because the normal passes through this point. Now if we substitute these values, this is what we get. As you can see, mu2 by v minus mu1 by u equal to mu2 minus mu1 by r. This is a very important formula and you must remember it. In fact, for any two surfaces, like when light gets refracted through a spherical surface, you can always use this formula, always, and you must remember it. Here mu2, is the refractive index of the medium into which the light is going. Mu1 is the refractive index of the medium, from which the light is coming. R is the radius of curvature of the spherical surface across which the refraction is taking place. V is the image distance and U is the object distance. If you take mu1 as 1, because the refractive index of air is 1, so if we put mu1 as 1, this is the equation you get. So that's it. We've derived the basic fundamental formula for refraction at a spherical surface.